To build a truly useful AI agent, it has to interact with the real world. That means getting it to seamlessly manipulate external systems. Right now, if you want your AI application to read a database, update a CRM, and scan a file system, you have to write, test, and maintain 3 completely distinct custom integrations. Scale that architecture up to 10 applications, talking to 100 different tools, and the math works against you. You are suddenly managing thousands of intersecting, incompatible connections, an engineering bottleneck that breaks under its own weight. The Model Context Protocol, or MCP, is the architectural answer to this hard-coded integration mesh. Originally released by Anthropic and now governed by the Linux Foundation as a vendor-neutral standard, MCP provides a unified approach to system architecture. It establishes a single universal transport language for any AI model to communicate with any external dataset or tool. Instead of maintaining a drawer full of proprietary single-use chargers, you switch to a universal port. The chaotic point-to-point mesh collapses into a clean hub-and-spoke model, routing universally to all tools. By standardizing the connection layer, you build a connector once, and any AI application can use it. The burden of integration shifts away from constant custom rewrites. This standardized connection relies on 3 core structural components that replace bespoke APIs: the host, the client, and the server. The host is the user-facing AI application itself, like the Cursor IDE or the Claude desktop application. Nested directly inside that host application is the client, acting as an internal router, natively speaking the MCP protocol. On the other end is the server, a lightweight program wrapping an external tool or database, exposing it to the client in a standardized format. This topology relies on runtime discovery. The moment the client connects, it sends a handshake. The server responds by automatically pushing a structured list of everything it is capable of doing across the connection line. This capability list is broken down into 3 categories. First are tools, which define the specific executable actions the model is permitted to take. Second are resources. These are read-only internal data sources, like your company wiki or specific project documents, giving the model context to read. Third are prompts, which function as reusable, standardized operating procedures and templates for specific recurring workflows. Because of runtime discovery, the AI application learns exactly what it can execute the moment it connects. There are no hard-coded integrations. It's entirely dynamic. A common misconception among developers is that MCP replaces an LLM's function calling capabilities or existing REST APIs. It does neither. Function calling is a capability of the model itself, the AI reasoning that a tool is needed and formatting a structured data payload. MCP is strictly the transport layer, routing that payload through the network to the tool and carrying the result back. Function calling and MCP operate as complementary halves of a single pipeline. The model decides to initiate a call, and MCP provides the network infrastructure. Your traditional APIs still perform the actual computational work. MCP simply layers on top of them to provide a universal discovery and routing mechanism. To see this pipeline in action, we look at the agent harness, the system architecture wrapping the raw LLM to manage memory, state, and execution. The model performs reasoning and sends its intent to the agent harness. The harness routes this intent straight through the MCP client to the correct MCP server. The server executes the task, and the result flows backward, injecting directly into the model's context window. The model remains the brain. MCP is just the standardized access badge that grants that brain permission to manipulate the real world. But standardizing access introduces a critical vulnerability. You are establishing a direct, automated pipeline between external servers and your sensitive internal data. This opens the door to documented attack vectors like tool poisoning, where malicious instructions are stealthily embedded directly inside a server's tool descriptions, waiting for the model to read them. There is also the risk of path traversal attacks. An unverified server could exploit the connection to expose thousands of internal applications, bleeding directly back into the LLM's context. Deploying this safely requires strict architectural rules. First, only install servers from verified publishers and mandate manual code reviews for any public server you connect. Second, enforce the principle of least privilege. Unless absolutely necessary, configure all servers to default to scoped, read-only credentials. Third, mandate human-in-the-loop approval gates for any sensitive or irreversible operations, whether that is writing to a production database or sending external communications. At an enterprise scale, engineering teams handle this by placing all MCP servers behind a centralized internal gateway. This acts as a strict filter, controlling exactly which agents can reach which servers. In agentic architectures, robust security guardrails and access controls provide the specific foundation required to scale AI systems safely. Depending on your use case, MCP servers are deployed in one of two distinct architectural flavors: local or remote. A local server runs directly on your host machine, communicating exclusively over a standard input-output pipeline, or STDIO, ideal for low-stakes operations. A remote server, however, is hosted in the cloud. It communicates over HTTP and requires standard OAuth authentication to access. Remote HTTP deployment is the enterprise standard for safely exposing commercial software products and production databases to external AI agents. Setting up either of these is highly efficient. Wrapping an existing dataset into a functional MCP server is essentially a 15-minute project. Using the fast MCP Python SDK, a developer only needs to write a standard Python function, complete with clear type hints and a docstring. Then you add a single line of code. Applying the MCP.tool decorator automatically transforms that standard Python function into a fully documented, discoverable MCP endpoint. The safest starting path is to build a local server wrapping a single read-only API. You can then use the MCP inspector tool to watch the AI call the code and validate the data flow manually. While large language models provide the raw reasoning intelligence, mastering the architectural plumbing of MCP is what actually allows those models to execute useful work in the real world.